And good morning, good afternoon, everyone on the line. This is Diane Podell. Thank you for joining the Cognitive Systems Institute Speaker Series. Today, I am happy to introduce Dr. Achim Rettinger. He's a junior research group leader at Karlsruhe Institute of Technology, which is in Germany, and it's one of Europe's largest technical universities. He studied, worked, or was a guest scientist at universities around the world, and he also worked at Siemens before joining Karlsruhe. His research focus is on developing innovative methods and tools in the area of machine learning and semantic web to extract and integrate knowledge across languages and modalities. Regarding cognitive systems, he worked in the research project called Cognition-Guided Surgery on a cognitive surgical assistant. Supported by the IBM Academic Initiative, he teaches a practical course where students implement applications using IBM Watson technologies. Today, he's going to present towards multi-step expert advice for cognitive computing. Achim, thank you for being our presenter today, and I'll turn the call over to you.
Yeah, thank you, Diane, for the nice introduction, and also thank you for inviting me, and also thank you, Jim, for inviting me. So welcome everyone to my talk. Since I have no idea what the audience is now, and the audience probably doesn't know me, I will give a very short introduction about myself and a little bit also about the research that we are doing in my group before actually talking about the topic that Diane just announced. So I wouldn't call myself a real like a cognitive systems expert. My background is in machine learning and knowledge representations, and I did a lot of like intelligent systems, but I wouldn't say that I have worked really on cognitive systems in the broader sense. So you just heard about this. This is me in the middle. It's my research group, and I'm working at KIT, Karlsruhe Institute of Technologies, one of the largest European technical research institutions with around 10,000 employees. And we are closely affiliated to the KSRI, that's the Karlsruhe Service Research Institute. That's the industry on campus model, closely affiliated to IBM and run by Professor Satzka. So there's a nice IBM connection there. Talking quickly about other research topics that we are mainly working on, and I'm totally happy to tell you more about it and discuss more about it. So just contact me after this presentation if you're interested in those topics. So that's for one thing, those cross-lingual technologies. So we are very interested in breaking down barriers between languages and modalities. So here on this figure, you see an example of entity linking across languages. So you start with different languages, you try to extract the entities mentioned in those different language texts and link them to one common language, or those cross-modal technologies where it's about cross-modal, for example, cross-modal information retrieval, where you search with an image for text or with a text for images, and so on. Then what we do in addition is semantic search. So we are working on search system where you can search with keywords, but keywords again in different languages. So you have a search query that contains words in different languages. You can search for documents in different languages that are not in the same language as the query. But we are mostly also doing this via searching with disambiguated entities, and I will talk about this later in the example that I will give in my talk. And we also do this searching across channels and modalities. So you can search with keywords inside news, social, and TV, and get results also across the modalities. So if there's images, you can also get those results. And the final example is entity summarization. So there it's about using knowledge graphs as background knowledge to summarize entities that are mentioned in text. Okay, then we also apply this in projects, so in innovation projects. One of those projects is called Exilim. You can check it out. The URL is there. One of the applications that we do there is a live augmentation of TV streams, where you can add tweets or news articles to a running TV show or do semantic search across the content and channels. Okay, and the final slide about the broader picture is the teaching. It was already mentioned, so I'm running for a couple of years now the Watson seminar that's supported by the IBM Academic Initiative here at KIT, and we had a lot of great student projects. Students like this a lot because they can easily implement a project and get results quickly. Some examples here is sentiment detection in images or classification of parties, political parties, and newspapers by their political affiliation. Okay, so this was the super quick introduction to what else I'm doing, and now I want to talk about one specific topic that I think is closest related to cognitive computing from the things that we have recently been doing here. And this is mostly joint work with Patrick Philipp, who is one of my PhD students. Okay, so let's get started. The motivation is that we are in all of the systems that I just showed you, we all often run into this problem that we have to run a pipeline of processing modules, right? Software components that need to run in a pipeline step by step and to solve a bigger task, right? We first encountered this problem in this project that was just mentioned, so where that is about medical assistance systems. So there it was about tumor progression mapping. So you have this brain scans of tumors, and you want to see over time how the tumor evolves. And this is basically a standard computer vision problem, but also those computer vision problems, they have a lot of small sub-modules that they have to execute in a pipeline or even in parallel, as you can see here. And you have also the situation that you can skip steps. Sometimes this improves, certain steps improve the pipeline, sometimes it's better to skip them. And it's really hard for human experts even that deal with this kind of problems every day to always know now which pipeline should I run and in which sequence should I run those steps. So we thought about maybe this is something where we should try to use some more intelligent methods than just hand manual fine-tuning of those type of pipelines. So maybe a little bit simpler application task that I will be using throughout the talk here is entity disambiguation. I guess everybody knows about this. So you start with a set of documents. Here in this case, it's web documents. And then you typically have a pipeline of tools, of steps that you apply so that in the end you find the mention of entities or concepts in those textual descriptions and link them to some kind of knowledge base, database, or knowledge graph. So here it's shown as DBpedia, Wikidata, or those are the ones that we typically use. The two steps that we identified here are named entity recognition and in the end the named entity disambiguation or named entity linking that are needed to solve this. So this task, if you look at this in a more abstract way, looks something like this. It's a little bit simplified to this tumor progression mapping task where we say, okay, we have a set of predefined steps N, and for each of the steps we have a set of experts available. And by expert, we mean those existing software modules that you can use to process data in each step. So those set of experts is different in every step. That maybe it doesn't, it's not clear in this illustration. So in every step, you might have a different set of experts and also a different number of experts, right? So again, going back to this natural language processing example of entity disambiguation, we listed here a few example tools that can be used to solve those two tasks, named entity recognition first, and then the outcome of named entity recognition can then be fed into a named entity linking tool. And we listed a few examples like Stanford Tagger or AIDA for named entity linking, and also the Exilim tool, which was developed in my group. Of course, Alchemy API would also be a good example for a tool that provides this kind of services. And there are frameworks like the Gerber framework that actually collect all of those services and try to compare them against each other. So this is one of those examples where you really have a lot of different approaches available and can test them. Okay, so why we started all of this research is that we made a few observations. The first observation was that the experts, or the different software modules that are available to solve each of the steps, perform very differently on different data sets. So if you, for example, have different domains, data from different domains, be it tweets or news articles, some experts perform good on tweets, others perform good on news articles, right? And if you don't have this kind of experience, which one works best when, you have to try, or you get suboptimal results, right? And then, so in terms of machine learning, speaking machine learning terms, the oversimplification here is that the data is not identically distributed that you get, right? It always has a different distribution and different characteristics. And this is really hard to capture if you want to offer optimal results with entity linking, entity disambiguation service. The second observation was that there is, if you decide on something like I want to do some simple ensemble learning or meta learning approaches, that you cannot just run all of the available software modules on all of the different steps, because the key problem is that after each step you get a not predefined set of unknown decision candidates. So with decision candidates, I mean, for example, the words that you need to link, right? So after the first step in the entity disambiguation task, you get a set of words that are supposed to be named entities, and then you need to decide to which knowledge graph entity I will link this kind of identified named entity. But every expert in the first step gives you a different set of potential candidates to link, and those sets are often also incompatible. So some build multi-word phrases that are overlapping and so on. So there's, in most cases, there's an infinite number of potential candidates that you could map. So it's not that obvious which one to pick. And running all approaches on all of the data is just not possible. So you need to have some way of being smarter in selecting what experts you choose in which step on which data set. Talking a bit about what's out there already in this area is, first of all, of course, the IBM Watson's cognitive computing capabilities from the original IBM Watson system. And there you probably remember those three key capabilities. That's natural language processing first. Of course, this, what I'm talking now, it's not specifically targeted towards natural language processing. Natural language processing is often a task that can be mapped to the problem that we are talking about, those expert processes, but it doesn't have to be. It can be, I've seen this tumor progression mapping problem and so on. What it's mostly about is the second part, this hypothesis generation and evaluation, specifically the evaluation part, since the hypothesis generation is basically done by the experts that we use in our system. What we are focusing on is evaluating which of the experts is best and how to combine them best given a certain data item. And all of this is certainly solved by a dynamic learning approach. So we try to learn weights for each of the experts depending on the context. And with context, we mean like the specific data point that we see. Okay, so of course in the academic area there's lots of research, previous research on this kind of problems. So first of all, there's the decision making with expert advice and bandits. Both of them are more focused on single steps, so they don't have this they only have this one-step optimization problems and don't have multiple steps typically. And for the bandits and Markov decision processes, which actually, of course, have those several decision steps incorporated, they typically don't explore multiple potential actions or executions of experts in parallel. So there's no framework that really captures the problem that we are trying to solve here. So what we did is we have a mixture of all of them and try to do something like a budgeted expert advice extended to a multi-step setting. Okay, so since there's not enough time to really introduce the formal definition of such an expert process, I go right into the example. And there again you see this task of entity disaggregation, and just imagine you would have something like a sentence, like a very simple case: Michael Jordan is a basketball player or plays basketball, and you want to identify the entities and link them in the end to something like those DBpedia entities Michael Jordan, right? And then you have experts in the first step that just first of all extract from the whole sentence the entities, so the potential entities, and this could be Michael Jordan or basketball. And in this case, there you see that depending on which expert you execute, you can have different results. So this is why there are different layers of results here. So it could be Michael Jordan and basketball. So Michael Jordan is detected as a named entity, basketball isn't, but in the next layer it could also be that Michael Jordan and another word is detected as a named entity, and so on. So you never know how many candidates you get here. And then in the following step, you can execute a different set of experts to then decide if you can link them to a knowledge graph entity and to which one. How we solve this problem now is we make use of probabilistic soft logic. That's a framework introduced by Kimmich and Bach. And what you do here is you introduce a set of rules, like logic formula rules, but they can be weighted. And once you train the system then with data, so you apply data to this to those rules, and then you can learn the weights and infer also unknown truth values that are unknown. So our idea was that this it's from the area of statistical relational learning. So this is perfect to actually capture the dependencies between experts and data points that we have in the setting, to really learn how they depend on each other. Again, coming from this observation that certain sequences of experts perform better on certain decision candidates. And by decision candidates, again, I mean something like a specific sentence, be it a tweet or a news article. So all we need to do is find those set of PSL rules, define them, collect observations of executions of the pipeline, and then do probabilistic inference to find out the weights that tell you how good an expert is in a specific state that is defined by a certain data point. So I also will not go into the details here, but I give you an example of what kind of meta dependencies we model here. So we have dependencies between experts and decision candidates in a specific state. So we have the state. So in the end, we want to find out which is the best state in the next step. Those are the two boxes on the right. and they depend on the previous state. This is the box in the middle. The expert for the previous state, that are the 3 boxes on the left, but also the experts available for the next step. So that's the E boxes on the top and the bottom. So and the question is, can we find a weight for each expert and decision candidate, telling us how good this expert is on each data point? So and what we do then is we define certain measures. So for example, hypothesis is one measure that we define, that's basically capturing which expert will result in which next state given the current state. So it's just taking the data, the history of the data, and finding out how a certain expert will act in a certain state. Then we have locality as a measure that's just predicting how good an expert is in a certain state. We have the weight. This is actually what we want to learn in the end. This is the true value of a certain expert in a state, the learned value. And we have value. This is then the combined average value of a whole state when the decisions of all experts are combined. And then we define those formulas on top of this, and examples of this is obvious ones like this locality, which just says the expected performance has a direct influence of the weight, which is obvious. Or the second rule is that the weight and the expected next state determines the value of the next state. So this is typical decision making under uncertainty rules. Then independence. This is a measure that is between experts of the same step, and what we want to capture here is that different experts might correlate a lot in the results that they are proposing. So we want to favor experts that are uncorrelated, so that we can execute them in parallel. So if 2 experts make independent errors in a different context, we might to choose both of them because they give us a lot of information for the next step, right? So they are not redundant. That's kind of what we're measuring here. And finally, we also measure the robustness. That's basically to account for future rewards. So robustness measures how well the upcoming expert behaved with outputs generated by the current expert. And this we also put in a rule so that you can have this kind of the intuition is you should choose an expert that generates outputs that allow expert in the next step to perform well on those outputs. Okay, so coming to the empirical evaluation that we did it exactly on this named entity recognition and named entity disambiguation task. We tested 2 scenarios. The first one is just evaluating every step individually. So what we did there is we trained the system on tweets and hold out a testing set from the training set, but we also trained on tweets, but evaluated on articles to test how well the learned weights can be transformed to a different domain. And then we also evaluated the whole pipeline, so the whole process. So those are some preliminary results. This is all things that's not published yet, and it's probably also not the final results, but you can already see that so those are in the 2 cases. It's for named entity recognition and entity disambiguation, each step evaluated separately. And we just, here we used some kind of simple majority, compared simple majority voting just on the average performance of an expert. This one is on the average performance of an expert given a certain data point. So this is already context dependent. And this is then, the PSL is then adding also the learned rules and weights on top of this. And as you can see in terms of F1 measure, the PSL outperforms the simple averaging and majority voting approaches for both of the tasks. But maybe the second scenario is even more interesting. there we compared the whole pipeline to other approaches like DBpedia Spotlight or AIDA. And you can see here we did this, that we trained on the microposts and with cross-validation evaluated on them, and there we outperformed in F1 measure and all of the other measures clearly the other approaches. But here for the Spotlight corpus, you can see that we trained on tweets only, but Spotlight is on news articles, and still we could outperform in terms of F1 measure something like DBpedia Spotlight, which is specifically tuned on the Spotlight corpus. So it's pretty impressive that this, or at least it looks like we can really well transfer knowledge across different domains. Okay, so the lessons learned here is this seems to allow for easy knowledge transfer, and it also scales pretty well as long as you have pre-calculated those measures and meta dependencies. So this is kind of the bottleneck here in terms of computational efficiency, but we haven't dealt with this problem yet. So we beat all of the state-of-the-art approaches for heterogeneous textual data, and what we didn't do so far is implement this into something like a reinforcement learning approach that is really about exploration and exploitation strategies. Right now, we are only applying this to existing data sets that are available, but we didn't care about exploring which data points to pick best to train the system, which reinforcement algorithm should be able to do. Okay, that's it so far. Here's the references that I mentioned throughout my talks, my own publications, and yeah, so thank you, and feel free to contact me about any of the topics, and now I'm looking forward to your questions.
Thank you, Achim. Audience, please press *1 on your phone to unmute your line to ask a question.
Hello, I have a question.
Yes.
Go ahead.
First, I want to say this is a very important and very productive process that he is developing, and I think we should thank him for the success he's pursuing. I need to understand in slide 26, however, what is the statistical significance of the differences that he shows?
Yes, I didn't report this here. Since we did a tenfold cross-validation, I think we should be able to report this. Since those are preliminary results, I guess we haven't just done the effort to report this, but at least in most of the cases, I would say it is statistically significant. But it has to be proven. You're absolutely correct.
Thank you, Martin. Are there other questions from the audience? We have just about a minute left.
Yeah,
Go ahead.
I had a quick question. Very impressive work. Kind of a question, have you considered practical implementations, or have you any experience with applying it to certain domains or kind of industrial implementations of this?
So since this is a very early results, we haven't thought about it much. I mean, we are applying this kind of named entity linking in a lot of settings. So this is, I would say, this has almost become a standard task that is available in a lot of commercial services, including Alchemy API and so on. So I would say the task itself has been proven to be important in many application areas. Since we think using this kind of approach, we can improve those class of tasks, especially in making them more applicable to a broader range of domains. We think this could have an impact also in more applied applications. But the work is too early to really say if this works. Yeah, but we will certainly try.
Well, thank you very much, Achim. This is very impressive. And audience, you have access to these slides. I have a link from our Cognitive Systems Institute website, and it has Achim's contact information. So we can also encourage you to continue the discussion on our LinkedIn discussion group. Achim, thank you very, very much for being our presenter today. And audience, thank you for attending. We'll see you next week.
Yeah, thank you a lot. And feel free to contact me.
Thank you so much.
Thank you.
Bye, everyone.
Thank you. Bye-bye.